Alright, so in this unit we're going to be looking at chemical equilibrium. And just so you know, we're going to divide this unit into two parts. This first part is going to be looking at reviewing the material, mainly the concepts. The second part we'll be looking at the mathematical applications, some sample problems, and we'll be giving the solutions as well. So, what is chemical equilibrium? Perhaps the best way to understand chemical equilibrium is by looking at graphs. So let's say we have the general equation substance A plus substance B goes to substance C and substance D. So if we're going to draw a graph of concentration, I'm just going to go ahead and denote it using that, versus time. So as A and B react to form products C and D, logically the concentration of the reactants will decrease. Let's go ahead and draw that. Concentration of A or concentration of B. Similarly, as the reactants react to form the products, the concentration of the products will increase. Concentration of C or concentration of D. Alright, so at some point we see that at least at the macroscopic level, the concentration of the reactants and the concentration of the products stabilize. There is no observable change. And at that point, which is about here, we reach equilibrium. The concentrations of the reactants, the concentrations of the products remain the same. They've reached equilibrium. Now, something important to point out here, and something that students often get, mixed up with, is chemical kinetics and chemical equilibrium. In chemical kinetics, we study the rate of reactions. In other words, we'll be looking at this portion of the graph. Whereas in chemical equilibrium, we're studying the point where the rate of the forward reaction is equivalent to the rate of the reverse reaction. In other words, where the concentrations at the macroscopic level remain the same. And so this point, I guess the region thereafter. And another way we could look at equilibrium is by looking at a graph of the rate of reaction versus time. And I was mentioning it in passing just earlier. So let's go ahead and construct that type of graph. Time versus rate of reaction. So again, we're going to go ahead and use the same reaction. Substance A and substance B react to form substance C and substance D. This is the forward reaction, and again, this reaction is reversible. So at the same time you have substance C and substance D reacting to form substance A and substance B. So looking at the forward reaction, we'll say it proceeds as such, and we're going to go ahead and label it reaction forward. And we have the reverse reaction. We'll label it reaction reverse. And so right here we see that the reverse rate of the reverse reaction or forward reaction equals the rate of the reverse reaction. And what this means is that at the microscopic level, A and B are reacting to form C and D. But at the same time, C and D are reacting to form A and B. And since the rate of both of those reactions are equivalent, the concentrations of the reactants and products remain the same with time. In other words, they stop changing. The system is at equilibrium. Okay, so those are the basics of chemical equilibrium. Really the, fundamentals of equilibrium and why certain reactants are at equilibrium. Now we're going to be looking at the equilibrium expression. Now the law of mass action states that the concentrations of all products multiplied together divided by the concentration of all reactants will yield the equilibrium constant. So let's go ahead and look at a situation where we apply the law of mass action. Let's go ahead and use the same general equation. Random substance A and B reactive C and D. Okay. So, as I was saying earlier, the concentration of the reactants, or products, in the numerator, I'm going to go ahead and multiply them. Now, something else to look out for here is you have the coefficients. The coefficients are going to go ahead and act as exponents. So this multiplied by the concentration of substance D, we have a coefficient which is just going to come right down as a exponent. Substance, now the reactants are in the denominator, coefficient as the exponent, substance A, concentration of substance A, you already have the exponent. And again, this value is going to indicate, or it's going to characterize how the forward and reverse reactions are in equilibrium with each other. And later on, we're going to be learning about the reaction quotient. And so it's very important that you don't get K and later on Q confused. K is looking at the equilibrium concentrations. Okay, so if this reaction is at equilibrium, there are going to be certain concentrations of products and certain concentration of reactants. And so again, last time I'm going to say it, K is looking at those equilibrium concentrations rather than, for example, initial concentrations that we're going to see with the reaction quotient. Now, there's something else that's very important to remember. We only include the products or the reactants whose concentration changes during a reaction. If a substance has a constant concentration during a reaction, which is the case for solids and pure liquids, they are not, and I repeat, not included in the equilibrium concentration. So let's look at an example. Let's say we have barium ions. Barium ions in aqueous solution with sulfate ions, aqueous solution, reacting to form barium sulfate solid. Okay, so here we have a solid. Its concentration during the reaction is now going to change. And so we don't take it into account in our equilibrium constant. Rather than have the concentration of barium sulfate, since it's a solid, we're just going to have number 1. And then we proceed as we did before with the reactants and the concentration of reactants in the denominator, coefficient of 1. We're just going to write it for the sake of note keeping times the concentration of the sulfate ions. Okay, there you go. Now, there are a few rules for the equilibrium constant. If you reverse the reaction, the equilibrium constant, you take the inverse of the equilibrium constant for a particular reaction. And that's sort of obvious. We just looked at barium ions plus sulfate goes to barium solid. If we're going to look at the reverse reaction real quick, barium 2 plus sulfate 2 minus solid. These are in aqueous solution. We see that it's the reverse of what we just had, which is barium 2 plus. So when you reverse a reaction, all you have to do to find the equilibrium constant for a reverse reaction, if you already know the equilibrium constant of the initial reaction, you just take the inverse. Okay. If you're multiplying a reaction by coefficients, let's say, you just multiply all these by 2, those are just going to show up in the exponents of those concentrations, where we have coefficient goes to the exponent, coefficient goes to the exponent, and so that's that. So now we have to look at something else. And that's if we're looking at the equilibrium constant of a gas phase reaction. We have a Kp value rather than a K value. Actually, before I go to that, I'd like to mention that the same concept is applied with partial pressures. There we were looking at the equilibrium constant using molar concentrations. But the same holds true, the same process, the same method holds true looking at partial pressures. Now we're going to look at, and so that's going to be important later on when we discuss Le Chatelier's law. Just real quick, I want to mention gas phase reaction. In that case, we have a Kp value. Kp value equals K R T delta N. K is the equilibrium constant using molar concentrations like we were just doing. R is a universal gas constant, 0.0821 liters times atmospheres. Temperature is the absolute temperature measured in Kelvin. Delta N is the moles of product gas minus the moles of product of reactant gas. And so that's also important in gas phase reactions. Okay, so that's that. Now we're going to take a look at the reaction quotient that I was mentioning earlier. Now the reaction quotient is found using the same method as the equilibrium constant. The only difference, and this is important, is that the equilibrium constant looks at, as the name implies, equilibrium concentrations, while the reaction quotient looks at the concentrations, or partial pressures, of initial concentrations. The relationship between the two is of utmost importance. It tells us which way a reaction will shift. Okay, so let's look at certain circumstances. So reaction quotient. Reaction quotient. I might be spelling quotient wrong. I apologize in advance. QUO. Okay. Reaction quotient we're going to denote with Q. Equilibrium constant is K. Okay. So if Q equals K. Again, I want to reiterate. Q relates the initial concentrations of products to the initial concentration of reactants. K is the equilibrium concentration of products to the equilibrium concentration of reactants. And so if Q equals K, if we think about it, let's just simplify here. The ratio of the concentration of products to the concentration of reactants at initial concentrations. If that is equivalent to the concentration of products, ratio of the concentration of products to concentration of reactants at equilibrium concentrations, what that means is that the products and reactants are already at their equilibrium concentrations. There is no shift in a reaction. It's already at equilibrium. Okay, simple enough. Now, let's look at a case where Q is greater than K. When Q is greater than K, the ratio of the concentration of products to the concentration of reactants at the initial concentrations before a reaction occurs is greater than the concentration of products to the ratio of concentration of products to the concentration of reactants at equilibrium. So let's look at our general equation: A plus B C plus D. What this means is that I have too many products. Too many. Okay? Now I have too few reactants in terms of concentration. And so in order to reach K, this must decrease and this must increase. Products must be consumed, reactants must be produced. And so the reaction shifts to the left. So Q greater than K, that means reaction shifts left. Okay. The final case is when Q is less than K. So let's go ahead and take a look at that. Q is less than K. In that case, the ratio of the concentration of products to the concentration of reactants is less than that at equilibrium. What this means is that we have too few or too little concentration of products. And this is simplified, of course. It's not just ratio of the concentration of products. Also depends on the reaction, the coefficients, but for the sake of simplification. So we have too few products. We have too much reactants, right? In order for this to change, this must increase and this must decrease. Reactants A and B must be consumed. Products C and D must be produced. The reaction shifts to the right. Okay. So that's a reaction quotient. That's a relationship between the reaction quotient and equilibrium constant. So just in summary, this is at initial concentrations. This is at the equilibrium concentrations. And so always keep that in mind so you don't get confused. The last thing we're going to be looking at is Le Chatelier's law. So Le Chatelier's law, and I'm going to quote from the Zumdahl textbook. If a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction to reduce that change. I'm going to say that one more time. It's very important. If a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction to reduce or oppose that change. So we're going to look at 4 different changes. We're going to look at the change in concentration of reactants or products. We're going to be looking at change in pressure, change in volume, change in temperature. Okay, so let's go ahead and look at the first one. Again, let's look at our equation. A plus B goes to C plus D. And again, Le Chatelier's principle, as I was talking about earlier. In Le Chatelier's principle, as I was talking about earlier, we're looking at the equilibrium, or reactions already at equilibrium. So if a reaction is at equilibrium and you add reactants, in order for that reaction to go back to its equilibrium concentrations, logically, the added reactants must be consumed and products produced. The reaction shifts right. Inversely, if you add products, that changes the equilibrium. It's no longer at equilibrium. Logically, the added products need to be consumed, and in this case, the reactants A and B produced, reaction shifts to the left. So you add reactants, reaction shifts right, add products, reaction shifts left. Okay, we're done with that. Let's look at pressure. Pressure and volume at the same time. They're related because, as you know, pressure and volume are inversely related. So there are three things that we're going to look at that can change pressure. And that's, number one, changing the concentration of reactants, products. And that's the same thing as we just looked at. So we've already mentioned that. You add reactants, shifts towards the products, add products in a reversible reaction, it shifts towards the reactants. Number two, add inert gas such as argon. And that has no effect on a reaction because inert gas does not participate in a reaction, therefore will not cause a shift in either direction. Easy enough. The third and last one is a change in volume. Okay, and so to understand the effect in a change of volume, we should be looking at or thinking about gas laws. PV equals nRT. Okay, let's say you decrease the volume. Because pressure and volume are inversely related, the effect is an increase in pressure. Now, the way this is counteracted, this increase in pressure, because if we're thinking about the equilibrium constant in terms of partial pressure, that's going to affect the equilibrium, right? And so if the partial pressure is increased, the way we counteract this change and the way the equilibrium constant or the equilibrium of the reactants and products are returned to the equilibrium, the concentration of reactants and products are returned to equilibrium is if we decrease number of moles. So let's look at the equation NO2 and N2O4. These are both gases. So when we decrease the volume, the result is an increase in pressure. Therefore, the reaction will shift in direction to reduce the number of moles so that the pressure decreases and the equilibrium pressures or the partial pressures are returned to the equilibrium pressures. In this case, the reaction will shift right. So decrease in volume, the reaction shifts in a direction in which there are fewer number of moles. Now, if both of these were 2, or just in any reaction where the coefficients are equivalent, there is no change whatsoever because reaction doesn't necessarily favor one or the other because it won't have an effect on the pressure. Now, in the cases where volume increases, you have a decrease in pressure. And so to counteract that, we increase the number of moles, which will increase pressure. Therefore, in this case, you increase the volume, the reaction will shift in the direction with the greatest number of moles, in this case, to the left. Okay, so that's Le Chatelier's principle or law. And there's one more part of it that we need to discuss, and that's how it relates to temperature. So number 4, temperature. Okay, so for temperature, we're going to be looking at the reaction for, I think, the Haber process, N2 plus 3H2 going to ammonia. So let's go ahead, N2, 3H2, NH3, and this is an exothermic reaction, about 92 kilojoules. Okay, so when we increase the temperature in an when temperature is increased, reaction proceeds in an endothermic direction. When a temperature is decreased, reaction proceeds in an exothermic direction. Okay, let's discuss the first thing I said. When a temperature is increased, reaction proceeds in endothermic direction. And this is because energy is added to a system. The reaction will therefore counteract that increase in energy by shifting in a direction to consume the added energy, and therefore it shifts in an endothermic direction. In this particular equation, the reaction is exothermic. If temperature is increased, we move in an endothermic direction, or this way. Now, inversely, if you remove energy, if temperature is decreased, we move in an exothermic direction, and therefore, in this particular reaction, the reaction shifts to the right in an exothermic direction. And so that concludes Le Chatelier's law, and I think we've covered all the concepts in this video. Shortly, we'll be posting a video with all the problems associated with chemical equilibrium. Till then, I bid you adieu. Have a good day. Tune in.